Thank you, Hong Kong, for supporting this conference, and especially I thank the organizers for changing the schedule so that I could talk before Kim Milton, because my talk is directly related to his. In fact, it is essentially a continuation of mine. The wording of my title may give the impression that I assume you already know all about the Powerwall model, what it is, and in fact, some of you have heard me talk about it about once every 2 years for perhaps the past 7, but others do not, so I have to spend a few minutes discussing where it came from. And in particular, since the thrust of this meeting is primarily toward experiment, or toward theory that's directly relevant to experiment, I feel called upon to give some justification for studying simple models that are clearly not realistic. I believe that the simple models still have things to teach us about questions of principle involving vacuum energy, some understanding of why there are infinities, what they mean in divorce from large doses of complication. In particular, studying the energy density at a point and the pressure at particular points of the boundary. The local quantities are physically meaningful and instructive, not least because they tell you where the infinities are and therefore provide a better understanding of their physical nature than a sheer discussion of the total energy would do. Also, the energy density and pressure are the source of the gravitational field, therefore of genuine physical interest. Also, I'm going to work with ultraviolet cutoffs and generalizations thereof, not with analytic regularization methods such as zeta functions and dimensional, which magically remove at least some of the infinities without much physical explanation or justification. These points, especially the last two, trace back to the seminal paper of Deutsch and Candelas in 1979. I think we're still building on their insight. So let me review a little bit about what we know. In the classic Casimir configuration of two parallel plates with the electromagnetic field considered in between, the Casimir energy density is constant, homogeneous. However, the electromagnetic Casimir energy near a curved conductor is not constant and can blow up as you approach the boundary. The scalar Casimir energy, even near a flat plate, is not. Therefore, we must first, the simplest case to study is the scalar field next to a flat Dirichlet boundary, referred to as the plate. Secondly, with no cutoff, and with the plate at the constant z, the expectation value of the energy and the expectation value of the pressure in directions parallel to the plate, after removal of the ubiquitous 0-point energy, turn out to be completely finite at each point, but they are proportional to the distance from the plate to the -4th, so that if you integrate them to get the total energy and the total force, those integrals will diverge. So first we should discuss what exactly these quantities mean physically and perhaps even mathematically, since if you are sharp-eyed you may think that my dimensions are inconsistent, but that's just because of notational conventions. So here they are again. And consider this situation where the solid line down here is the plate at z equals 0. At x equals 0, I have another boundary which you can think of as another plate, although I'm not going to calculate its effect, or you can think of it as just an imaginary boundary, a test plane. Then if you work it out, we'll see that there is an energy density that builds up near the plate here, which is constant as far independent of x. So if you move the plate along a little bit, you get a linear increase in the total energy of this, cut off somewhere, some arbitrary point in the distance. And the force, F is the total force on the surface, E is the total energy per unit area, and everything is divided out by per unit length in the y direction. So trust me, everything turns out right in the end. The dimensions are right, although they don't look like it. Okay, the big problem that arose concerns what's called the principle of virtual work. The force on the test surface should equal the decrease in the total energy behind the surface as the surface moves a unit distance. So the force should be equal to, up to a minus sign should be the derivative of the total energy with respect to L, where L is the coordinate where the surface is. In this situation down here that we're looking at, that just says that F should be equal to minus E. Since E is independent of X, and E total is the integral over all X, the differentiation just strips the integral sign off. And without the cutoff, that's exactly what you find out formally, because point-wise, the pressure is equal to the negative of the energy density. And so if you ignore the fact that the integrals of these things are divergent, you would say this is exactly satisfied. But now here comes the big problem. If you put in an ultraviolet cutoff and look at a constant non-vanishing ultraviolet cutoff, don't take the limit, it turns out that F is not equal to minus E, it's equal to plus 1/2 E. This is what I call the pressure anomaly. When I was a postdoc in London in the 1970s, my roommate and co-worker was Steve Christensen from the University of Texas, who had just finished a PhD thesis on the expectation value of the energy momentum tensor in curved space. And what he found in a very complicated summary page, which takes up an entire page of physical review, is that if you make the ultraviolet cutoff covariant by considering a separation of points in an arbitrary direction of space-time, the results are very highly dependent on the direction of the splitting, including the divergences in some of the finite terms. So immediately it was recognized that this is a phenomenon of the same nature, except that it has to do with a boundary rather than the bulk curvature of space-time. And the relationship between P and E depends on the direction in which you separate the points to perform a regularization in the vicinity of the wall. If you choose what I call the neutral direction, that is the direction that is neither perpendicular to the plates, nor in the time direction, nor in the direction of the particular component of parallel pressure that you're looking at, then you get the result that you expect, that F is equal to minus E. But that seems rather ad hoc, doesn't it? So we began a program of looking at a more, I won't say realistic, but a less ad hoc way of introducing the cutoff. Consider a simple model that is non-singular, so there will be no infinities except the obvious ones that come from integrating over infinite volumes. Where simple means, as I stated at the beginning, I don't want at this stage to solve the exact electromagnetic problem for a physically realistic conductor. I want some other kind of a model that introduces a cutoff in some physically consistent way. So just introducing a point-splitting cutoff and leaving the cutoff parameter finite, which was the original idea, turns out to be unsatisfactory because of this pressure anomaly, which, by the way, has nothing whatever to do with anomalies the sense of trace anomalies, conformal anomalies, chiral anomalies, and so on. But it seems clear that this anomaly is coming up because of a defect of the regularization scheme, which is if you have a model that's non-singular from the start, comes from a consistent Lagrangian equations of motion, surely this phenomenon should not occur. That was the hypothesis when we began to look at it. And we chose the model of Klein-Gordon, a scalar field with a potential, or you may say a Klein-Gordon mass, which is 0 in the half of space and then rapidly rises as some power of the rest of the space. This is chosen simply for calculational convenience and because it has the right qualitative behavior, not because of any feeling that it should have any real physical significance. Alpha is some positive number. We can assume it's an integer without loss of generality. And as alpha increases to infinity, the potential normalizes is here rapidly approaches a boundary at z equals 1, not z equals 0. When alpha is small, an integer, alpha equals 1 and 2, then the problem can be solved exactly. We're really interested in what happens for large alpha. So one could solve this problem by separation of variables, as I would teach my undergraduate students, and then the equations would satisfy, the eigenfunctions would satisfy equations like this. But it's more convenient, especially for numerical calculations, to build a Green's function. In particular, what's called a reduced Green's function, where you use Fourier decomposition in the time direction and the transverse space directions, but not in the direction where the non-trivial dependence occurs. And for that case, to build the Green's function for the ordinary differential equation, we need the solutions with the opposite sign here. That's nice because they will decay rapidly rather than oscillating, and so you can integrate over them. So let me briefly set up a little bit of a notation here. Consider functions that go to 0 as z approaches infinity, and functions that go to solutions that go to 0 as z approaches negative infinity. Since the potential is 0, we know that h must be proportional to e to the kappa z for negative z. Then you can construct the Green's function as you always do for an ODE, and it will be a product of the things divided by the Wronskian. If we make a particularly nice choice of, or natural choice of normalization, the Wronskian can be computed in closed form. And for x1 and 2, as I said before, the solutions are standard special functions, area functions and parabolic cylinder functions, respectively. For alpha greater than 2, even an integer, they aren't. And so our strategy is let's develop approximation methods for general alpha and test them against the cases alpha equal 1 and 2 where we know the answers. So we make the usual kinds of approximations, WKB approximation for large z, or equivalent also for large kappa. This would be good if either kappa or z is large, or both. But if kappa is small and z is small, then we need something else. So we can do perturbation theory in kappa. This was the theory was developed by Jeff Wagner. When kappa equals 0, the equation can be solved exactly in terms of modified Bessel functions, and we can then continue solving by iteration to get the first order approximation, and if necessary, higher approximations. Construct the first order solution in the usual way of such a perturbative problem, and go from there. So we're now ready to look at the expectation value of the stress tensor outside the wall. In that region, the solutions are purely exponentials, and so we can write down the exact formula for the Green's function, which depends on the potential only through this reflection coefficient gamma, which depends on f prime at z equals 0. This part up here is just the Green's function for empty space, so that produces all the divergences and nothing but divergences, so you can ignore it and just look at the second term. And we need the basis functions inside the wall only to calculate gamma minus. So now for small kappas, we can use the perturbative solution. For large kappas, we can use the WKB solution, but there's a gap in between where neither is correct. So what we do is to approximate it by the exponential of a linear function of kappa and choose the coefficients a and b in there and the joint points d1 and d2 to match it against the perturbative and the WKB solution, and choose those numbers so that the functions and the derivatives match at both ends. And so in here, I can't put the legend and the graph on the slide at the same time. Well, let me just show you and then explain. Over here, the perturbation, the green curve is the perturbative approximation, which is good at small kappa. It's superposed on the gray curve. You can't tell the difference. This one over here is the WKB solution. You can see that there's a region in between where neither of them is very good. The spline is the red dashes, and the gray curve here is a solution that we did numerically, which purports to be the exact solution. This is for alpha equals 6, so I don't have an exact solution available. I just have this numerical approximation, but it's close enough to the spline to give us some confidence that the spline approximation is doing the job it's supposed to do. Now, after cutting a long story short, there's a formula for the energy density which we can now evaluate, and because we now have gamma minus, so we can do this integral numerically, and we'll get in here it is for alpha equal 1, the approximation is dashed, and the exact solution is in solid gray, so it looks like it's doing fairly well. Notice that when z approaches 0, there's a singularity. And remember, the wall was supposed to develop at z equals 1, not at 0. So this is a little bit of an embarrassment when it first happened. It was easy to understand what's going on. It comes from the fact that the potential is not differentiable at the origin. So there's some diffraction of that. And anybody who's done the WKB approximation for potential that has a singularity will understand what's a discontinuity or discontinuity in the derivative will understand what's going on there. And an advantage of going to large alpha is not only that you get a good wall at z equals 1, but also that the singularity at z equals 0 weakens. So this should go away at larger alphas, and in fact for alpha equals 6, I didn't put the slide in the top, but there you'll find that, oops, that this actually goes down and has the finite intercept. Okay, so tomorrow Kim will talk about what happens inside the wall, which results in a number of technical difficulties, which I won't go into since I'm running out of time. The renormalization theory, or the potential inside the wall, needs to take account of the fact that we have a non-trivial potential, and so there will be local bulk divergences, which are relatively well understood compared to the things that are associated with boundaries. And so the renormalization theory, as Kim will report, works out actually quite well. And going back to the originally motivating problem, both outside and inside, as predicted, there is there is no indication of a pressure anomaly. So in that sense, the project appears to be successful. We want to work out what happens on the inside. The work that I've done with Kim Milton and his associates is based largely on the WKB approximation, so it doesn't treat the bottom of the spectrum accurately. My student assistants and I are now working on that, developing these spline methods to try to apply them on the inside. And we're also trying to improve the wall, replacing the test wall by an actual Dirichlet boundary, or even better, another soft wall to see what happens. And since I'm out of time, I will not read the conclusions to you, but just get to this slide to stress that this work builds on the work of 3 student generations of mostly undergraduate students who have, in particular, the graphics I reported were primarily by Colin Whistler, and the new student, Tommy Settlemeyer, discovered mistakes in that, which we quickly were able to repair. And also involved here the group in Oklahoma, and particularly, as I mentioned before, Jeff Wagner, who was once a graduate student in Oklahoma, then briefly a postdoc with me, and is now at Lawrence University. And I think I should stop there.
Questions?
So, first, you see a force outside of the wall, essentially.
Say what?
So you have a constant potential, and there is a boundary,
Right.
and your energy changes, which is what you would find also for, which is if the pressure, what it would look like. That's a real question, actually. So is it normal also for a Casimir cavity? I'm not sure. If you had a normal Casimir cavity where you have a shell boundary or a Dirichlet boundary and a Dirichlet boundary, and then in between you would ask what the energy is, would it also change continuously?
I'm not sure I understand the scenario.
What I'm
You're
surprised
saying
you see
if I
force.
take you're asking what happens if I have 2 walls?
Usually I would see no
Which are
force.
soft?
I would see no force inside the 2 walls, only on the walls, right? That's a standard case. I would see force only on the wall, usually.
Right.
And you see a force within a constant profile.
Well, there's always a non-trivial, a non-zero value of the expectation value of the stress tensor. But it's hard to interpret physically unless there's a boundary there for it to be acting on. I think we just have a semantic dispute.
I would ask you.
Right. People want coffee, huh? Okay, so thank you very much. We reconvene in 20 minutes, 5 past.